So, have you ever written two different pieces of code that do the exact same thing, and then you're just staring at them wondering which one's, actually better? If you've been there, you've already been wrestling with the main idea behind Big O notation. Today, we're going to crack the code on this super fundamental concept. It's basically the language we all use to measure performance and write some truly efficient software.
All right, here's the game plan. We'll kick things off with the efficiency puzzle itself. Then we'll figure out how to kind of ignore all the background noise so we can really define what Big O is. After that, we'll see it in action, talk about why it's so important, and then at the end, we'll take a quick look beyond just the upper bound to get the full picture.
Okay, let's dive right in. We're starting with the problem that, let's be honest, every single developer runs into, the efficiency puzzle. Just imagine it. You've coded up two different solutions to the same problem. They both work, they both give you the right answer, but how do you really know which one is better? I mean, which one is going to scale well? Which one is truly the more efficient, faster solution when you throw a ton of data at it?
Well, to answer that, we can't just, pull out a stopwatch. That's not going to work. The results would change based on what computer you're using or what language you're writing in. No, instead, we've got to start thinking a little more like a mathematician. We have to learn to ignore all that distracting environmental noise.
So here's the key. We have to zoom out and look at the big picture. We're not worried about the exact nanoseconds an operation takes. What we really care about is how the runtime behaves as our input, we'll just call it n, gets really, really big. Is the time it takes going to grow nice and steady, or is it just going to explode? We do this by intentionally ignoring all the small stuff, like how fast your specific processor is, so we can focus on just one thing, the fundamental growth trend of our algorithm.
And, to talk about this high-level growth stuff, we need a shared vocabulary, a common language. And that language is Big O notation.
To put it as simply as possible, Big O gives us an upper bound. Think of it as the worst-case scenario. As your input gets bigger and bigger, Big O tells you the absolute maximum rate your runtime is going to grow. It's like a promise. We guarantee your code's performance will never, ever be worse than this.
Okay, and this graph right here? It shows the idea perfectly. See that kind of wiggly line, the one labeled Tn? That's your algorithm's actual runtime. It's messy, it's what happens in the real world. Now look at that smoother curve right above it, the CGN. That's our Big O function. Now for small inputs, everything to the left of that vertical line, we don't really care how they compare. But once the input n gets big enough, you see our actual runtime is always trapped underneath that upper curve. It literally provides a performance ceiling. So this slide gives us the formal math behind that picture we just saw, and don't let the notation scare you. All this is a really precise way of saying what we just saw on the graph. Our function's runtime, t of n, is Big O of g of n. If we can find some magic multiplier c and some starting point n0, where after that point, our runtime is always less than c times g of n. It's just the official mathematical way of defining that performance ceiling.
All right, that's enough theory. I think it's time we get our hands dirty with a real example, just to see how this all comes together in practice.
Okay, let's take this function, 100n squared plus 20n plus 5. The question is, can we prove it's O of n squared? Well, our goal is to show that it's basically trapped underneath some version of n squared. And here's the trick. We can be a little generous. We can find an upper bound for the smaller parts. For any n that's 1 or bigger, we know that 20n is going to be less than 20n squared, right? And 5 is definitely going to be less than 5n squared. So let's just substitute those bigger values into our expression. Our function is now less than or equal to 100n squared plus 20n squared plus 5n squared. And when you combine those, what do you get? 125n squared. And boom, just like that, we found our ceiling. We've proved it's O of n squared with a constant RC of 125.
And going through this process, well, it shows us a really simple and incredibly powerful rule of thumb.
And it's this. What really matters is the fastest growing term. When n gets huge, that n squared part just takes off like a rocket, with so much force that the other smaller pieces, the 20n and the 5, they're just left in the dust. They become totally insignificant. So that one dominant term, it ends up dictating the entire growth curve.
So, we know how to spot the fastest growing part of a function. But why do we care? What's the point in the real world? Well, it is all about finding the bottleneck in your code.
And that brings us to honestly the most important question of all. How does all this abstract math actually help us write better, faster programs?
Take a look at this. Imagine your code runs in 2 steps. Phase A is pretty quick, it runs in O of n time. But then there is phase B, and it's a total snail by comparison, running in O of n squared time.
Since these two phases run one after the other, the total time is completely dominated by the slower one. The whole algorithm gets slapped with an O of n squared label. Big O instantly points this giant flashing neon arrow at phase B and basically screams, right here, this is your bottleneck. If you want to speed things up, you know exactly where to put your effort. And this isn't just theory. I mean, think about a social media feed trying to sort posts with an O of n squared algorithm. Your users are just going to be staring at a loading spinner, and then they're gone. That's the real-world cost of a bottleneck.
But Big O is really just one piece of the puzzle. It tells us the worst-case scenario, that performance ceiling. So let's take a quick peek beyond that upper bound to get a more complete picture of what's going on.
Turns out, Big O has a sibling, a counterpart. While Big O gives us the upper bound, the performance ceiling, there's another notation called Big Omega, and it provides the lower bound, or the floor. It answers the exact opposite question. What's the absolute best-case scenario? How good can this possibly get?
Now, every once in a while, you get a situation where the best-case and the worst-case scenarios grow at the same rate. When that performance ceiling and the floor are basically the same, we have a special name for it, Big Theta. This gives us what we call a tight bound, and it means we know exactly how the algorithm is going to perform as it scales. It's really the most precise description of an algorithm's efficiency you can hope for.
And that all brings us to our final thought. Big O, Big Omega, and Big Theta. They are incredibly powerful tools for understanding the fundamental performance limits of the code we write. They really define its speed limit as the problems get bigger. So I'll just leave you with this one question to think about. Your code has a speed limit. Do you know what it is?